Okay, welcome to lecture. We'll get started here in just a sec. And we're continuing on with gases in that chapter. Okay, we last time started talking about gases and gas laws, and we ran through a number of them last time. And grab something here. Go. We talked about a couple important ones, or several actually. We talked about, let's see here, where can I write this? I'll use this space. We talked about the relationship between basically pressure, volume, and temperature, and sort of the different laws that go with those. First one that we talked about was Boyle's law, and Boyle, we had P1 V1 equals P2 V2. This was at constant temperature. The pressure and volume here doesn't really matter in terms of the units as long as they're the same. But what we saw here is the relationship that as the pressure goes up, the volume goes down, and vice versa. As one goes up, basically the other goes down. We also saw Charles' law, which is V1 T1 equals V2 T2. This one would be at constant pressure. And as we talked about, basically to maintain that constant pressure, what happens in this situation is the volume pretty much adjusts. So as the temperature goes up, the gas molecules are flying around faster, and we would expect an increase in pressure. But in order to basically stop that from happening, the volume will get larger to give everybody more room and keep the number of collisions pretty much constant and keep the pressure constant. And vice versa, if we lower the temperature, then everybody's flying around slower, going to cause less collisions and a decrease in pressure if nothing occurs. So to keep the pressure from dropping, the volume will come down. So the relationship we see with Charles' law is as the volume goes up, so does the temperature, and as the volume goes down, so does the temperature as well. Sort of Guy-Lussac's law, which is a similar type of relationship. P1 over T1 equals P2 over T2. This would be at constant volume. So unlike sort of in Charles' law, where the volume does move to allow the pressure from changing, here the volume is fixed, which means as the temperature increases, we are going to have more collisions. The volume's not going to adjust or anything like that, and that's going to cause a rise in the pressure. So as the temperature goes up, so does the pressure in the situation, and as the pressure or temperature goes down, so does the pressure as well. The important thing here, like pretty much all gas laws, as we've talked about, is the temperature. Temperature does need to be in Kelvin in order for everything to be right. So you do need to add 273 to the Celsius to convert it to Kelvin. We also saw Avogadro's law, V1 N1 equals V2 N2. And this is at constant temperature and pressure in that case. And the volume is obviously any volume you like in terms of units, as long as they're the same. N is the number of moles. And what we talked about here is basically the moles and the volume are sort of proportional to each other. And again, you could just use this like a normal gas law, kind of plug in the values and solve for whatever you're looking for. We also saw this sort of a consequence of this relationship under constant temperature and pressure is you could also use sort of Avogadro's law with stoichiometry. And again, instead of doing sort of a mole-to-mole relationship like we do in a traditional stoichiometry type problem, you could use a sort of volume-to-volume relationship if you're dealing with gases. Pretty much, if you're using a gas law, temperature does need to be in Kelvin. So pretty safe bet. Any gas law that you come across, you need to convert it to Kelvin before you use it. And as we talked about as well, even if they give it to you, for example, in degrees Celsius, and they ask you to give the answer in degrees Celsius, you do have to convert it to Kelvin when you put it into the gas law. So you got to always pretty much go Kelvin on most things in chemistry. So only like really one or two things where you don't need to get into Kelvin, but usually Kelvin, pretty safe thing that's which the temperature needs to be in. Now, sort of putting all these guys together, we get sort of the big gas law, which is our ideal gas law. And our ideal gas law is our PV equals nRT. And our ideal gas law is a little different than the other ones, as we talked about last time as well. Again, here, not really like a before and after, so not two or something. So you pretty much have one sort of situation occurring. And it is actually the most restrictive in terms of the units as well. So when you use the ideal gas law, pressure has to be in atmospheres, volume has to be in liters, and obviously needs to be moles. Temperature does need to be Kelvin here, and that's really because of R, which is a gas constant, 0.08206 liters atmosphere Kelvin mole. So R is a number you always have, and as we talked about last time, sometimes people will round it and do 0.0821, which is okay as well. But it has all those units, the gas constant. So in order for them to properly cancel out, everybody else has to be in those specific units. So ideal gas law is sort of a one situation, but definitely the most restrictive in terms of units. You need to have everybody in those correct ones. A couple other things we talked about as well was the idea of STP, that is standard temperature and pressure. And that is a pressure of 1 atmosphere and a temperature of 273 Kelvin. So if you're given conditions for STP, that's essentially what it means in those things. And we also saw that at STP, you definitely could use the ideal gas law, but if you are at STP, 1 mole of any gas will equal 22.414 liters. So that's a conversion that you could sometimes use to sort of avoid using the ideal gas law again if you're at STP conditions. If you're not at STP conditions, then you cannot use that conversion. You do have to use the ideal gas law. And lastly, I think we talked a little bit about units, obviously, at the beginning, and that relationship is 1 atmosphere is 760 torr and 760 millimeters of mercury. So the 760 there is an important number. It's really the conversion factor to go between those units. And probably in the most case, those are the 3 most common units that you come across. There are other units like we talked about, like pascals, kilopascals, PSI, pounds per square inch, also bar and things like that. So any questions on any of that stuff I think we covered last time? Oh, I think we missed one. So, the one that we're actually looking at, the problem here, which is the combined gas law that we also talked about. So that's the one we use on this example we're actually writing on. And that is the one that does with all of them, P1 V1 over T1 equals P2 V2 over T2. And again, that is sometimes referred to as the combined gas law. And that's the one I think we finished up on last time. That sort of deals with all 3 variables together. And again, the one that gives people sort of the hardest time in terms of rearranging. But same sort of rules here for this one. Pressure and volume really can be any unit you want as long as they are the same on both sides. So all the units cancel correctly. Temperature here, again, like everything else, does need to be in Kelvin. Any questions on any of that stuff there? So we're going to talk then about a couple of properties of gases and sort of how we can calculate a couple of these properties of gases. And let's get to that, I think. So let's talk about density calculations that involve gases and also molar mass. So density, as we've talked about before, is mass over volume. And we have this formula here to calculate the density of a gas. And as we talked about, typically densities of gases are usually in grams per liter is typically the units that we use, not grams per milliliter or grams per cubic centimeter, but grams per liter is typically what we use. And you could basically get that is equal to P, which is the pressure, times the molar mass divided by RT, which is your gas constant, and your temperature in Kelvin. So basically to sort of calculate the density, you do need a couple pieces of information like the pressure, the temperature, and the molar mass of the gas, and you could do that. The molar mass is another thing that we could actually calculate, and if we calculate the molar mass, we can calculate the molar mass, which again, units of molar mass are grams per mole, right? Which are the typical units of molar mass. And we can use basically the molar mass is equal to the density times RT divided by P. Here again, the density does need to be in grams per liter for everything basically to cancel out. Now, really, both of these sort of formulas that we see here on the screen are really based off of the ideal gas law. And you could use something like the ideal gas law to help you sort of solve for each of these things if you can't remember these actual formulas here. So you could kind of use it to sort of figure that out. So let's just say we wanted to know, you know, what is the density of methane gas at, say, 755 torr and 27 degrees Celsius. So why don't you give it a try first, and then we'll talk about sort of how we could do that and see what you come up with. So take a minute or so, a couple minutes here, see what you come up with. And we're looking for the density in, we'll do grams per liter. I'll get a calculator because I made it up myself. Okay, so you could either, again, you could use sort of the formulas that we saw on the previous slide and sort of plug in the numbers. But again, in case you can't remember those formulas or something like that, hopefully you'll be able to remember the ideal gas law. And you can actually use the ideal gas law here to help you out. So if we take, say, for example, PV equals nRT, and if we take the ideal gas law and actually solve for N divided by V, so if we do that, we're going to divide the RT to the other side, going to take the V to the other side and divide it. And if you do all that, you will end up with P over RT. Now, you may be saying, how is this going to help me? If we think about the units of N is moles, and the units of volume is liters. That is moles over liters. That is actually, by the way, the molarity, right, of this. It's basically what we would be solving for here. So we could use the ideal gas law and basically solve for molarity, which is moles per liter. And we could do that because we do have the pressure given to us and we do have the temperature. And then obviously R is a constant. So that would be, what we would, it's all we need basically, is all the information we have. Because this is really based on the ideal gas law, we do need to do some conversions. So we're going to take our 755 torr. We're going to divide it by 760. And that will get you 0.993, we'll call it 0.993. We also need to convert our temperature like normal into Kelvin. So we're going to do a 273 on that. And that's going to give us 300, I believe. 300 Kelvin. All right, so if we actually do put it into here, our pressure would be 0.993. Our R, 0.08206. Or again, you could use the rounded version there if you like. And our temperature, which would be 300 Kelvin. Again, in terms of units, atmospheres cancel, Kelvin cancel. You have liters over mole, which will then flip to moles over liters when you divide it. And if you do that, you will get should be 0.0404. Again, the units here are moles per liter, which is close to what we're looking for. But we actually want the density. We don't want the molarity, which is basically what we got going on right there. We want the density in grams per liter. So at this point, it really is just a conversion factor. If you think about units, we have moles per liter. We basically need grams per liter. So what's left to do is convert the moles into grams using the molar mass from the periodic table. So if we go to the periodic table and get the molar mass, which is 12.01 plus 4 times 1.008, gets you something like 1604 grams per mole from the periodic table. Moles are going to cancel. That's going to leave us with the units we're looking for, grams per liter. And if we do that, 0.0404, we get something like a density of 0.648 grams per liter. So what I did here is basically what that formula that we saw on the previous page tells you to do. And as you can see here, hopefully that it does come really from the ideal gas law. So the point here is, if you can't remember those two formulas on the previous page, you should just think about the ideal gas law and think about sort of conversions and units, and really just do some units and stuff like that. So could always sort of fall back on that ideal gas law and probably be able to figure out the answer to, a question that you're looking for. Any questions on that? Okay, so I think you have another one here. See what you come up with. Let's take a look here. Perfect. So why don't you give this one a try? Take a couple minutes here. We got 2.1 liter vessel. contains 4.65 grams of oxygen, of a gas, not oxygen, of gas, and it has a pressure of 1 atmosphere and 27 degrees Celsius. We're looking for the molar mass here. So see what you come up with. Molar mass, again, in units of grams per mole. So again, a reminder, grams per mole. All right, so take a couple minutes, see what you come up with. Okay, so let's take a look at this. And let's see what we could do on this particular problem that we're looking at. Again, here you can use that formula that we saw in the previous couple of slides back and just sort of plug it in there. But if you are in a situation where maybe you can't remember it or something like that, again, in this problem, even though we're solving for the molar mass, which is different than the density that we did on the previous slide, we can still use sort of the ideal gas law to help get us there and look at the or figure out the molar mass. So let's see sort of that approach again with not using that particular formula there. So again, if we just think about the molar mass, which is what we're trying to solve for, we're looking for grams per mole. And in the problem, we have 2.1 liters, which is a volume. We obviously have grams given to us here. We have 1 atmosphere, which is a pressure, and we have 27 degrees, which is a temperature. So in terms of the molar mass, which is what we're looking for, we actually have one part of it right there given to us right there in the problem. We actually don't have to do very much in terms of that. So again, in the situation, this should help you sort of focus and go, well, I need the moles part. how can I get the moles part? And again, this is where, if you can't remember that formula, you could think about the ideal gas law. And if we just kind of mark off the other pieces of information that's given to us, we have the volume, we have the pressure, we have the temperature, and we always have R. So looky there, we can find moles, which would be the bottom part of what we need. So again, here you can, if you can't remember those sort of formulas that we saw a slide or two ago, the ideal gas law is a good equation or formula there that will help you get to the answer. So in this case, we do just want to solve for N because that's sort of the missing piece that we need, which would be PV over RT. And I think, let me take a look here. The only thing we have to worry about is the temperature that needs to be converted. So we're going to take 273 plus our 27, should give us 300 Kelvin. And now we have everything that we need to put into here. So the pressure would be 1 atmosphere. The volume would be 2.1 liters. R would be 0.08206. And of course, our temperature here in Kelvin at 300K. And if we do all that, we will get we'll call it 0.0853. And the units here are going to be moles, as everything else cancel. Liters will cancel, atmospheres will cancel, Kelvin will cancel, leaves us only moles. But that's okay in this particular case because that was the one piece of information we were missing. So now we can solve for the molar mass by taking the grams that were given to us in the actual problem, divided by the moles we just figured out. And that will get us 54.5 grams per mole, which would be our molar mass. There's a point there. So 54.5. So again here, as you can see, we did the density one previously, where if you sort of cannot remember that formula, you could just go into the ideal gas law and use it to solve it by kind of following the units. And same thing here, if you are looking for the molar mass, again, the ideal gas law is the formula that you can use. And that's really because those two formulas that we saw in the previous couple of slides, they really are based off of obviously the ideal gas law. So the root of how you get to those formulas are the ideal gas law. So if you forget them, you could use the ideal gas law to help you out. Any questions on those calculations there? Okay, so we've now talked about how to calculate density for gases, how to calculate molar mass. So we're going to kind of come back to our favorite thing as well, which is stoichiometry. So we're going to talk about stoichiometry that involves obviously gases and sort of the approach to solving stoichiometry problems that involve gases. And the approach really to solve those sort of problems that involve gases in terms of stoichiometry is really the same approach that we take for any type of stoichiometry problem. Like usual, we want to make sure that we have an equation that's balanced. We want to convert to moles. We want to do the mole to mole relationship, and at the end, figure out something. The main difference is really, in most cases, I won't say 100% of the time, but probably 90% of the time, the main difference of what you do is you're interested in perhaps a gas, and you're interested in some information about a gas. So it's very common that we're interested in something like a volume of a gas that's produced. And the main difference of what you do with these type of problems is at the end of the problem, instead of maybe using like the molar mass from the periodic table to figure out how many grams you produced or something like that, we oftentimes will somewhere along the way in a gas stoichiometry problem has to throw in there PV equals nRT. So somewhere along the way, usually you'll need to use the ideal gas law. And like I said, probably about 90% of the time, you would use the ideal gas law at the end of the problem. You could potentially use the ideal gas law at the beginning of a problem. And if you did, you most likely would be solving for moles, right? Because at the beginning of a stoichiometry problem, you need to get everybody into moles. So if you use it at the beginning of the problem, moles is most likely what you would probably be solving for. If you're going to use it at the end of the problem, which is probably most of the time how you'll use the ideal gas law at the end of the stoichiometry problem, you most likely will be solving for V, which means usually you'll be given some information about the gas, and you can then plug it into the ideal gas law at some point. So let's take a look at one here together and sort of see what's going on. What is the volume of CO2 that's produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose are used up in this reaction? So obviously we have an equation, which is sort of step number 1, right, in a stoichiometry one. We then want to take whatever they gave us and convert it into moles. So they did give us a lot of information. So just sort of where we're going is we're ultimately interested in our CO2, which is a gas. We're starting with this guy, which obviously is not a gas. So because we're looking for the thing that is a gas, all this information about sort of pressure, temperature should go with it. So we do have the pressure of it, which is 1 atmosphere. We're looking to solve for the volume. We also have the temperature, which is 37 degrees Celsius. So you could kind of see the ideal gas law is sort of coming about here. We have P, we're looking for V, we have T, we always have R. So we're sort of missing N for CO2. And how we're going to get the moles of CO2 is from the other piece of information that's given to us, which is we're starting with 5.6 grams of our glucose. So we're going to basically use stoichiometry to go from grams of glucose to moles of glucose, and then moles of glucose to moles of the CO2. So this problem will start like a normal stoichiometry problem. We're going to have our balanced equation. We're going to take our 5.6 grams of our glucose, and pretty much we need to convert it into moles. Now, we would go to the periodic table and do that, and it looks like we got 6 carbons at 12.01 plus 12 hydrogens at 1.008 plus 6 oxygens at 16. Looks like we get about 180.2 grams per mole. So we're going to take 180.2 grams per mole of our glucose. And if we do that, 5.6 divided by that gets us 0.0311 moles of our glucose. So the very first part here, very much like a traditional stoichiometry problem, we're going to use the periodic table and the molar mass. We're going to convert the grams to moles. But again, we're not interested in glucose, so we want the stoichiometry part, and we can see from the equation for every 1 mole of our glucose, we are going to produce 6 moles of CO2. So we're going to use that as our conversion factor. That's going to allow us to go from moles of our glucose to moles of CO2. So it was 6 moles of CO2 and 1 mole of our glucose. I'll just write glucose here. And we will get times 6.187 of CO2. And if you remember, that was essentially the missing piece that we needed for our CO2. So now that we have the moles of CO2, we could find the volume by using that ideal gas law and solving for V. So V would equal nRT over P. So putting that stuff in, let's go here. I'm gonna borrow that page, I think. So V equals, again, our PV equals nRT. So our V equals nRT over P. So the moles that we had was 0.187. Our R and our temperature, which I'm getting old, so it was 37 degrees Celsius. So we need to convert that by adding 273, gets us 310 Kelvin, divided by our pressure, which was 1 atmosphere. So that makes it easy. 1 atmosphere. Again, atmospheres will cancel, Kelvin will cancel, moles will cancel, going to leave us liters. And it looks like we will end up with 4.74 liters of CO2 would be produced in this case. Actually, kind of like our theoretical yield in liters for CO2 would be produced. So hopefully what you can see here is it is really the same sort of 4 steps there. We're going to balance the equation. We're going to convert to moles. We're going to do our mole to mole relationship. And we're going to take those moles and convert to some other units. Again, the difference here is at the end, we stuck it into our ideal gas law. Any questions on that? Okay, so you have another one there. Why don't you see what you come up with? As I sort of wrote over it, of course. So let me erase some of that. You can actually see it. Get rid of some of that. There you go. All right, so take a couple minutes and see what you come up with here. So I erase some of that so you can see. All right. We're looking for the volume of hydrogen gas at STP in this reaction. You might need magnesium. Magnesium is 2431 grams per mole. Okay, so let's take a look and see. So we're looking for the volume hydrogen gas, which is this guy. If we started with 5 grams of this guy, so obviously we have an equation. We're going from one thing to the next, so it's sort of a stoichiometry problem. It's at STP, so a reminder that STP means that the temperature is 273 Kelvin, pressure is 1 atmosphere. So if you just kind of think about what we got going on here, we do have pressure, temperature. We're looking for a volume. So again, you can think about your ideal gas law here. So pressure we have, temperature we have. We're looking for a volume. We always have R. So just like before, in terms of the hydrogen gas, which is obviously what we'd be interested, we are missing the moles. But we do have the grams of magnesium. So this is where the stoichiometry will come into play. We have an equation. It's balanced, I hope. Yep. And we want to take the grams of magnesium, which we're not interested in. We want to convert it into moles using the molar mass from the periodic table. And if we do that, we will get .206, it looks like, moles of magnesium. And again, the purpose of this is going to allow us to go from magnesium to hydrogen gas, which is what we're interested in. And we can see from the equation that it is a 1-to-1 relationship, which means 1 mole of magnesium will give me 1 mole of H2 from the equation. And that's the stoichiometry part, which I think I could do that math there. That is 0.206 moles of H2 in this case. So at this point, we can go into the ideal gas law if you choose. PV equals nRT, which means V would equal nRT divided by P. Our N being what we just calculated for our hydrogen, our R being our gas constant, our temperature, which is 273 because it's STP, and our pressure, which is 1 atmospheres because it's STP as well. And if you do all that good stuff there, gets you a 4.61, and the units here would be liters as everything else cancels out. So again, sort of our same steps here. Step 1, balance equation. Step 2, convert to moles. Step 3, mole to mole relationship. Step 4 here, using the ideal gas law. Now, when you look at this problem, this is one way you could solve it. And perhaps you might remember that we talked a little bit about a situation that occurs at STP. And because this is at STP, we could have, if we wanted to, use that relationship that 1 mole of any gas is 22.414 liters, which means once we got to this part, we did not have to use the ideal gas law. We could have just took 0.206 moles. And again, because it's at STP, we could have said 1 mole is 22.414 liters. And we will get the exact same answer, hopefully. 4.61 basically, again with rounding, maybe 4.62. But if I didn't round, I would have the same answer, 4.61 liters. So this is a situation, as we were talking about, that because it is at STP conditions, you do not necessarily have to use the ideal gas law here to get the volume. You could use that conversion factor. But it also demonstrates the fact that if you can't remember to use it, or you're not sure you should use that conversion factor here, you could still go into the ideal gas law and get the right answer. So again, in this case, there was a couple different ways you could solve it because it was at STP conditions. Any questions on that there? Okay, so as you can see, hopefully from these examples, stoichiometry involving gases, pretty much the same deal. The only difference is, again, somewhere along the way, usually the ideal gas law comes into play. As we talked about with regular stoichiometry, as we talked about with solution stoichiometry, and even gas stoichiometry, you could still also have a limiting reagent type problem as well. So kind of a little rarer in that case, but you could sort of have one. You don't usually come across too much of that, but potentially you could have that. All right, so the next thing we're going to talk about is partial pressures and Dalton's law of partial pressures. And this comes about because very often gases come basically as mixtures of several different gases together. And when we think about what happens when we sort of introduce more gas molecules to a container than, say, just one, it can have sort of an effect on the pressure, if you will. So for example, here, if we look at container one, the only gas molecules basically flying around in container number one is the red molecules. And that means that they would be the only gas molecules that would exert some pressure, which means really in the case of this first one, the total pressure should equal the pressure of the gas molecules that are red because they're the only ones flying around. Same thing if we go to the second container there. The only gas molecules flying around in that container are the green ones, which means if we were interested in the total pressure of that particular container, it would be all as a result of the green gas molecules basically flying around. But now if we put them together, both containers, we would have our red gas molecules flying around. We would have our green gas molecules flying around. They both would cause collisions. They both would contribute to the pressure. So the total pressure when we kind of put them together is basically the sum of each of them. So in a mixture of gas, this is what is known as the partial pressure. So the partial pressure of gas one are the red ones in this particular case, and the partial pressure of gas number two are the green ones. In this case, if you add them together, which is why they're called partial pressures, because they each contribute to the overall pressure, that will get you basically the total pressure of that gas mixture. Now, how do you sort of get the partial pressures? There's a couple different ways you could get the partial pressures of gases, but honestly, the most common way is, again, our good friend ideal gas law and solving the ideal gas law for P, basically. And when you solve the ideal gas law for P and you solve for sort of a partial pressure, the idea behind this is a couple of things. Like we see in the third picture there, they're all flying around in the same container, which means for the most part, they all have the same volume. So the volume for every gas in there, if we were going to figure out the partial pressures of the red gas and the green gas, the volume for both of those would be the exact same. And most likely that container there on the right is sitting in the same room on the same counter at the same temperature. And that means that the temperature for both gases would be the same as well. And if you just think about what I just rearranged here, the volume is the same for both. The temperature is the same. R is a constant. So really when you're trying to figure out the partial pressures of gases, really the only thing that usually will vary for each of the gases is the number of moles of those gases that are flying around. Now, although they are in the same container and they're flying around, one of the things that makes something sort of an ideal gas, which is sort of what we're talking about here, something that makes it an ideal gas is the idea that there is no attractive force or repulsion type force, no attraction or repulsion between different gas molecules, which means although you have red ones flying around that container, although you have green ones flying around in that container, you could almost treat each of those gases as if they were in there by themselves. So the red guys that are flying around are not affected at all by the green gas molecules and vice versa. And that means that we essentially could do two separate calculations. So in the case that what we're looking at, I would take the ideal gas law and solve it for the red gas molecules and solve for P for the green gas molecules. And then to get the total pressure, you simply just add those numbers together. If you had 3 gases, you would do it for 3 and add them all together. So like I said, probably most commonly easy way to figure out total pressure from a mixture of gases is using the ideal gas law. Again, solving for, excuse me, solving for P for each of them separately and then add them together. Now, there is a situation where perhaps you may not be given enough information to use the ideal gas law. So perhaps you're not given, the temperature, the volume, whatever that may be. So there is another way that you could calculate sort of partial pressures and total pressures, and that's using something that we talked about, I think, in the previous chapter, which is mole fraction. So we can use the mole fraction to help us determine partial pressures and total pressures if we don't have enough information by using this equation here. This is the partial pressure of a gas. This is the mole fraction of that gas. And that is the total pressure of that mixture. So if you remember, we talked about mole fractions, and here's an example of that. Remember that X is the mole fraction. And basically, to figure out the mole fraction, it pretty much is not a percentage, but it's similar. So we take the moles of what we're interested in. So in this case, we would be interested in the moles of A, and the guy that's circled, divided by the total number of moles. The only difference is we don't multiply by 100. So in a situation, if it's like a partial pressure type problem, and you're like, I don't have enough information really to use the ideal gas law because I don't know temperature, volume, or any of those type of things, but I am given something like perhaps grams of the gases or something like that, or moles of the gases, and maybe a partial pressure or maybe a total pressure given to me, you can use sort of this secondary approach here to figure out what you need. So that little guy in the box there is sort of an important one. Again, it allows you to figure out partial pressures, total pressures with kind of limited information given to you in a problem. Any questions on that there? All right, so why don't you give ones a go here? Let's see what we got. We got 5 grams of helium as added to 5 grams of neon. We're looking for the partial pressures of each gas in that mixture and also the total pressure. So why don't you take a few minutes here and see what you come up with. We're looking for 3 answers, 2 partial pressures and a total pressure. And neon is, what we got there, helium and neon. So helium is 4.003 grams per mole from the periodic table, and neon is 2018 grams per mole. All right, so give that a try. You're welcome. All right, so let's see how we're doing. So we're looking for the partial pressures of both of these gases in this mixture, and we're also looking for the total pressure. So again, we can think about sort of the ideal gas law here. Our PV equals nRT. And we do have the volume given to us. We do have the temperature given to us. We always have R. So as we talked about before, essentially we could do P is equal to nRT divided by V. And really for each of the gases, in order to use this, we are missing the moles. But that's okay because we do have the grams of each of them. So we could use the molar mass basically to get the moles of each. So if we did the moles of helium, that would be 5 grams divided by 4.003 grams per mole. And that would get us 1.25 moles of helium. We would do the same thing for neon. So our moles of neon would be our 5 grams divided by the molar mass from the periodic table for neon, which was 2018. That's going to get us 0.248. And again, that pretty much will now give us all the missing pieces that we need for the ideal gas law for each of them. Our volumes in liters already, so that's okay. Like usual, though, our temperature there does need to be converted. So our temperature is going to be 273 plus our 27, going to be 300 K. Now what we could do again is solve for P for each gas separately. So let's kind of put a little line there. If we take the pressure, partial pressure of helium, that again would be nRT over V, which means we're going to take the moles of helium, which is 1.25. We're going to use our gas constant. We're going to take our temperature in Kelvin, all divided by our volume here, which is 2.5 liters. If we look at the units, everybody's going to cancel out except for atmospheres, which is good because we're looking for a pressure. And we do that. We end up with 12.3 atmospheres, I think, if I did that right. All right. That would represent the partial pressure of helium. To figure out the partial pressure of neon, we'd be pretty much the same calculation. The only difference is we're going to use, obviously, the moles of neon here. So that's going to be 0.248 moles times our R. And times our temperature, all divided by our same volume since they're sitting in the same container. And if we do all that, we end up with 2.44 atmospheres. So the 12.3 would be the partial pressure of helium. The 2.44 would be the partial pressure of neon. And now to find the total pressure, we basically just add those together. So the partial pressure of helium plus the partial pressure of neon, which gives us 12.3 plus 2.44 atmospheres. It gets us 14.7 as the total pressure of that mixture. Any questions on that part there? We see in this example, and we'll see why that is a little bit later on in this chapter, but we see in this example that the major contributor here to the pressure is helium. Yeah, so helium is actually the major contributor here at 12.3 versus neon, which is 2.44. And pretty much the reason for that, as we will see later on in this chapter, is the molar mass of each of those. Helium is much lighter. So since helium is much lighter, it's going to be able to fly around a lot faster, which obviously is going to result in more collisions than the slower moving neon, which is heavier. So it's not going to be moving as fast. And again, that could be causing less collisions. Is why we see sort of the difference there. Any questions on any part of that calculation there? So hopefully you could also see that although it's the fancy word partial pressures, it really is still sort of using the ideal gas law. It's just really kind of separate ideal gas law problems that you just add up the pressures at the end. Any questions on that there? So that is one type of partial pressure. Let's take a look at another example here, which might be a little bit different, and see what you come up with. So let's do that one. A sample of natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure of the gas is 1.37 atmospheres, what is the partial pressure of propane? So why don't you take a moment or two and try to think about solving this and see what you come up with. Okay, so let's take a look at this one. So in this particular case, we have three gases that are in this mixture, and we're not given a lot of information in this problem. We're given basically the moles of everybody. and we're given the total pressure of that mixture. So in this particular case, we really don't have enough information to use the ideal gas law, right? So to use the ideal gas law, we need some temperature, which was not given. We need some volume, which wasn't given either. So this is a case where we need to use sort of that other formula, which was like the PI equals XI times PT. This being the partial pressure of a gas, the mole fraction of that gas, and the total pressure. Now, this formula, we do have enough information because we have the moles of everybody, so we can figure out the mole fraction. We also have the total pressure, which will allow us to figure out the partial pressure here. So the first thing we want to figure out is the total moles, and that's pretty simple. We're just going to add everybody together here. Gets us... And if we add all those moles together, we got 8.24 plus 0.421 plus 0.116, 8777 looks like. So in this particular case, we're interested in just the propane, which is this guy. So to figure out the mole fraction of our propane, we're going to take the moles of the propane. We're going to divide it by the total moles. Again, we're not going to multiply by 100 because it's not a percentage. We get 0.0132 as our mole fraction, which is this guy. They gave us the total pressure, which is this one. So that means to figure out the partial pressure of propane, we're going to take our mole fraction. We're going to times it by the total pressure. And if we do that, go with 0.0181 atmospheres. Now we could have, if we wanted to sort of do it for the other ones as well. It didn't really ask, but we could have, for example, got the mole fraction of methane, right? Which would be higher in this case, right? 8.24 divided by 8.77 gives us 8.24 divided by 8.777, something like 0.939 is our mole fraction. And you can do the same thing. So the partial pressure of methane in this case would be 0.939 times our 1.37 gives us like 1.29 atmospheres. And you could do it for the last one as well. Or at this point, since the last one is the only gas left, you could add these pressures up and subtract. So if you want to kind of quickly figure out the pressure of this, we know the total pressure is 1.37. We know 1.29 of it is methane. We know 0.0181 of it is propane. So if we just subtract those, gives us 0.0014 as a partial pressure of the last one. Or you could do the mole fraction and obviously add it like you did the other two as well. What's up with that? Any questions on that? And stuff. I think I might have. Yes, you might bad calculator here. That's actually should be 619. That's better. 0.0619 for the last one. Any questions on this type? So this is a very kind of convenient one. It essentially is the percentage of each of these without doing by 100. So this is very useful. Again, if you're not given enough information to go into that ideal gas law, you could use this to basically figure it out. And again, a reminder, my last one there should be 0.0619 as the partial pressure for ethane. All right, so let's then talk about another sort of partial pressure situation that can develop. So far we've sort of seen a regular one where you can use the ideal gas law. We see one where you don't maybe have enough information and you need to use sort of the mole fraction. A third way that sort of partial pressure problems come about is a lot of times it occurs based on sort of how the gas is collected in an experiment. So for example, if we have this setup here, which is a common experiment that's done, we take some potassium chlorate, we're going to heat it up, we're going to decompose it, and we are going to produce oxygen gas in here. So that's what's in here. It's test tube, it's potassium chlorate. As you heat it, the oxygen gas goes through the tube and it comes into this jar. And this jar is usually pre-filled with water to the brim. And basically as the gas comes in, the water goes out. So it sort of displaces the water and you end up with sort of this empty spot over here. And that empty part of the container is actually not empty. That's actually where the oxygen gas came in. So it's actually filled with oxygen gas, although it looks empty. But because of the way this reaction was done, or this experiment was done, we collected this gas in the presence of water, right? And when we do this reaction, going to generate some heat and all that, and some heat and water is going to heat up the water. And in this empty spot that's here, in addition to the oxygen gas in this particular example, which is what we're interested in, we also will collect another gas, and that is water vapor will get collected. And that's just a result of actually physically sort of doing this experiment and collecting the gas in this fashion, which means in this area, the total pressure, as you can see here, is the pressure of the oxygen gas, which is what we're interested in, and the pressure of water. And this is what is sometimes referred to as the vapor pressure of water. And usually the vapor pressure of water is a value that you can find on a table. You can look it up based on temperature. And this creates really a partial pressure situation because in this area where we're collecting the gas we're looking for, we now have two gases. And in most cases, we are not interested at all in the water part of it, which means in order to sort of figure out the pressure of the gas we're interested in, which in this particular example is oxygen, we basically need to take this equation and rearrange it. And the partial pressure, for example, of oxygen, or just generically the gas you're interested in, is the total pressure minus the vapor pressure of water. So we essentially need to subtract off the vapor pressure of water to sort of get what is sometimes referred to as the pressure of the dry gas. So sometimes people refer to it as the pressure of the dry gas in this situation because you're subtracting off the contribution of water to the overall pressure. And in most experiments, again, you're not interested in the water part of it. You're really just interested in like the oxygen gas in this case, hydrogen gas, whatever gas you may be collecting. Is really the one you're interested in. So usually you have to do this sort of correction value or factor, which is essentially just subtracting off, that vapor pressure of water. Here's a chart or table, not from your book, but you have a similar one where you can, as you can see, look up basically the vapor pressure of water at a specific temperature. Also in the back of your lab manual, I think there's a big table as well. But usually that value is either given to you in the problem or it's a value that you can sort of look up. So to sort of see a partial pressure problem that involves sort of that, we have a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the oxygen gas? So the key a lot of times to know that you need to do this sort of subtraction about water vapor is in the wording. And in the wording of the question, it says something like it was saturated with water vapor. It will sometimes say it was collected over water. So those are key words. You see something with water, gas, collecting. Usually what that means is you have that situation happening. So as we see here, the total pressure again would be the pressure of the oxygen, which we're interested in, and the vapor pressure of water. So since we're interested in oxygen in this example, the pressure of oxygen, or partial pressure of oxygen, again would be the total pressure minus the vapor pressure of water. This is a value that you could find in that table we just saw, or a table like it. And so it was given to you because we're doing this at 30 degrees Celsius. So we looked up the value at 30 degrees. So really in this one, we just need to plug it in. They gave us the total pressure of 753. We need to subtract off the vapor pressure of water. So vapor pressure of water. And if we do that, we will get 753 minus 31.824, 721 torr. And this would be the pressure of oxygen gas, again, dry gas sometimes it's referred to. But they did want it in atmospheres, so a reminder that to convert to atmospheres, we would need to divide by 760. And if we do that, 0.949 would be the pressure of our dry oxygen gas in atmospheres. So the good news is this type of partial pressure one is usually pretty simple in that sense. You just basically need to subtract off the contribution of water, or the vapor pressure of water from it. So it's not too bad. And again, in this case, we did oxygen, but where there's the partial pressure of oxygen, it's really any gas you're interested in that's collected in this fashion. You could do a similar calculation. Any questions on that? Okay, so we will stop here for lecture. This will also conclude everything that will be on the exam. We'll stop at this point. So through partial pressures, we'll save the rest of it for some other day. We'll continue lecturing obviously on it tomorrow, but it will not be on the exam. So everything on the exam, which is in 2 days, right, is up through what we just covered today, okay, in terms of chapter 8. Obviously, everything from the previous chapter is still good to go, but through what we covered today, we'll be on the exam on Thursday. Any questions on that? Okay, so the exam, like I said, is still going to be on Thursday. And through this point, today we're going to talk about part 2 of the titration experiment. And then you could go off and watch part 2 and do the calculations for part 2. And we will start in about... we'll do about 9:50 or so there, since we went a little bit long here for lecture. So about 9:50, you'll see everybody in lab. If you didn't type here, please do so. And I'll see everybody in about 20 minutes or so.